And so I'm really happy to, so first of all, hello everyone. It's a bit of a deja vu moment because so most of you know who I am. Most of you are glad, but for those who are not, my name is Nashir Contractor. I'm a faculty member in your department here, Industrial Engineering, Com and Kellogg. And I wanted to introduce you again, welcome you to our first Sonic Speaker Series event, to the best of my knowledge, post-pandemic.
Wow.
So it is something that we put on pause for quite a long time. But we used to have an active Sonic Speaker Series before the pandemic. In fact, we may have had one literally a week before we shut down. But I'm thrilled to have a chance to do this. My goal in the Sonic Speaker Series is to look for people who are young, talented, shining, so that you get to know them before they become super famous. They're already famous enough, but before they become, so that's it's sort of early career stage folks that we look at, etc. I can also tell you anecdotally that many of our students who often will recommend to me, as was the case for you, who we should bring in as Sonic Speaker Series invitees are often the same folks who then end up getting jobs through the contacts they make. Yes, there's a lot of knowledge that is gained by having visitors, but also other sort of social and long-term network connections with those individuals. Today, we're delighted to have with us Hancheng, who's getting his PhD at Stanford with a primary appointment in the Department of Computer Science, but also in management science and engineering, which is a department that we have Liz Gerber here, who got her PhD in that department in Stanford, and does really interesting work on computational social science, human-computer interaction. Has got his undergraduate degree, like a lot of folks, present company included. I got my undergraduate degree in electronic engineering from Tsinghua, and then decided to do more work, and has worked over the last several years with lots of really illustrious collaborators at places like at Oxford and MIT, Sandy Pentland, and other places, and now he's doing really exciting work at Stanford. And so we've been following his work quite closely. I know Megan has been using it. We were very happy to have him join us here today because he's actually giving a talk tomorrow at a conference in downtown Chicago for the annual conference of the Society for Industrial and Organizational Psychology, SIOP, where we have a panel on looking at how to study teens from a text standpoint. That Megan has organized as a panel that SIOP is here in downtown tomorrow. So without much further introduction, I will say that speaking of the fact that I mentioned earlier, that people who are here, often students will talk to these folks and often get jobs for it. You, in this case, are on the job market yourself this year.
Yeah.
And so, spread the word. We know how weak ties are very important in helping get jobs, etc. So who knows who you'll meet where, who will help you with those kinds of opportunities. But with that, I will hand things over to you. And again, thank you. Join me in welcoming Hancheng.
Yeah, thanks so much, Nosh, for the super kind introduction. And I'm also super glad to be here to be talking about my PhD dissertation. And feel so fortunate that I become the very first speaker of the pandemic at Sonic Lab. Yeah, that's great. So let's get started. So today I would like to talk about my work on evaluating and designing computing systems for the future of work. Okay, now it's working. So I like to start with this question. What computing technologies would amplify human collaboration and decision-making? Well, this is actually some questions and something that someone from 120 years ago started to think about. This very person, Arthur Mee, is a writer. And he says, as it is said to be not unlikely in the near future, the principle of sight is applied to the telephone as well as that of sound, Earth will be introduced a paradise, and distance will lose its enchantment by being abolished altogether. As you might have guessed out, he's talking about something like video conferencing. And 120 years later, now we indeed have video conferencing tools We have Zoom, we have Microsoft Teams, and we also have instant messaging apps at workplace like Slack to help us get even closely connected. And more recently, we have sophisticated hardwares like AR and VR to help us have better experience at workplace. And of course, we have this wave of generative AI like ChatGPT, which drastically changed the way we work, significantly improve our productivity in many ways, and in sometimes even our creativity. And the question really becomes, given all these advances, have we developed the ideal workplace technologies? Are we living in a paradise as suggested by Arthur Mee? Well, the landscape is really vague and unclear. There have been mixed views on current workplace technologies. On one hand, there are positive sentiments. For example, this New York article, someone is saying, distance matters much less now. Because of technology these days, we are actually inching closer and closer to replicating the office. And we have news with titles like this. Why is Zoom suddenly everywhere? It's easy and fun to use. On the other side, there are negative sentiments. Another article in the New York Times has this title, Why Zoom is Terrible. And I would argue the debates on the usefulness of computing technologies, they're actually not unique to workplace scenarios. It also applies to many other scenarios as well, such as education, relationship, and health, where people have been arguing back and forth with each other whether technology is being helpful or not. The thing that I've become really curious about during my PhD is instead of arguing back and forth with each other, how do we navigate such disagreements on technologies and make progress? Well, the answer to that probably lies in this very argument. I would say that it's perhaps time to think about computing technologies as a science of the artificial. And this particular term is actually proposed by Herb Simon. And some of you might know him. He's kind of like a pioneer in many different fields, including artificial intelligence, organization theory, decision-making, and many others. And he has written this book titled A Science of the Artificial back in 1969. And this book is centered around how artificial phenomena ought to be categorized. And Simon discussed whether such phenomena belong within the domain of science in a similar way as physics or math. Specifically, Simon wrote, natural science is knowledge about natural objects and phenomena. We asked whether there cannot also be artificial science knowledge about artificial objects and phenomena. And in this book, Simon gave the high-level picture about some important factors that could contribute towards the science of the artificial. So there are empirical evidence, technical methods, and design he emphasized throughout the book. In terms of empirical evidence, Simon wrote, the contingency of artificial phenomena has always created doubts as to whether they fall properly within the context of science. The general problem is to show how empirical propositions can be made at all about systems. And in terms of technical methods, throughout the book, Simon emphasized the importance of modeling, simulation, and many other techniques. And finally, in terms of design, Simon wrote, it's important to study not only how things are, but also how things ought to be. As a computational social scientist and human-computer interaction, my PhD research has been largely influenced by this vision. And I have been trying to approach towards the science of artificial with this three particular approach. And in terms of empirical evidence throughout my PhD, I've been asking and answering things with regard to how can we leverage increasingly available large-scale data to study machine behavior and human behavior over computing platforms. And in terms of technical methods, I have been interested in asking and answer, how can we better model, sense, and predict machine behavior and human behavior? And finally, in terms of design, I'm interested in things like, how can we design applications that align with our needs and values with powerful computing technologies? And with that, I have been collaborating with people in many different disciplines, including computer science, like human-computer interaction, natural language processing people, but also people from management science and sociology, as well as people beyond academia from big tech companies, startups, and nonprofit organizations. And workplace technologies has always been my core interest during my PhD. Well, I have been working on some other things as well, but I think workplace technology is perhaps something that has been influencing everyone and has been proven to change so much in the past 5 years. So I have been publishing mostly in human-computer interaction venues, but my broad interest has also led me to doing some work in sociology type of journals, as well as recently trying to conduct some works oriented towards general audience. And today, I'd really like to focus my talk, around these 3 different visions towards building a science of technology. And specifically, I would like to talk about workplace technologies with 3 representative work to demonstrate these 3 different types of approach. And in terms of empirical evidence, I would like to talk about my work on large-scale analysis of multitasking behavior during remote meetings, which we have been leveraging millions of online meetings, millions of emails and file edits, try to make sense about people's remote meeting experience. And in terms of technical methods, I would like to talk about my work, how we have been using data science and AI and try to classify and predict ahead of time how the team is going. And finally, in terms of design, I would like to talk about our recent work and how we have been using large language model to re-envision the way researchers conduct research, where we have been using large language model to generate scientific feedback in a way that is similar to peer review, and using that to augment the current practices of research feedback. And with that, I would like to dive into specific projects. So the very first project, large-scale analysis of multitasking behavior during remote meetings, is a project that I did in the early days of the pandemic in collaboration with Microsoft Research. And this particular research is motivated by something that we encountered almost every day back then, where people have been talking a lot about experiences such as Zoom fatigue, meeting engagement, productivity, not only in public outlets, but also in academic journals. So our goal in this particular work is try to achieve a systematic understanding of this very notion of remote meeting multitasking behavior. Why remote work and remote meeting? I don't think I need to spend much time here, but basically, remote work is an essential mode of work across industries, and it has become so important ever since the pandemic. And central to remote work and remote meetings through video conferencing tools, which help team members stay connected, collaborate, and function as an organization despite physical distance. And multitasking behavior is something social scientists has been studying for quite some time. It refers to performing more than one task in parallel in rapid succession, and has been shown to closely link to one's productivity and well-being. Multitasking is an important meeting experience. As we have experienced, it's quite ubiquitous on the remote meeting kind of context where people have been doing lots of different types of tasks like checking emails or other types of things. Yet there is a lack of an understanding to our particular work when, how, and why people engage in multitasking behavior on the remote meetings. Prior works on multitasking over computing platforms, they're generally limited in coverage, although people have studied that for quite a long time in different disciplines, from psychology to communication to human-computer interaction. Yet many of those works, they look at 10-ish or 20-ish people and doing some kind of observational study, how they have been doing this kind of task switching. And to contribute to the literature, here in this work, we seek to perform a large-scale analysis of multitasking behaviors through mixed methods. And here are a number of questions we seek to address here. First of all, how much multitasking is happening during remote meetings? Secondly, what factors associated with multitasking during remote meetings? Thirdly, what do people do when multitasking during remote meetings? And finally, what are the consequences of multitasking during remote meetings? And here's the approach that we used. It's a mixed methods design. The first part of it includes a large-scale regression analysis, where we have been using possibly collected data from telemetry to measure and try to reflect objective patterns at scale. And to augment this particular data analysis, we also conduct a qualitative diary study so as to capture the nuanced experiences and motivations behind why people multitask. And let's talk about the telemetry data analysis first. The data set that we use, it comes from Microsoft. It includes meeting-related action from Microsoft Teams, email usage data from Microsoft Outlook, file edits data from SharePoint, and we, in total, collected 4 separate week-long snapshots from February to May 2020 for all Microsoft US employees. And through these data sets, we derive features such as meeting duration, meeting size, meeting types, hour of the day of the week as features. And after that, we join the 3 different data sources by unique user identifier, which in this case is Microsoft user ID. And for each meeting user pair, we label it as email multitasking if the user was found to have at least 1 active email action during the meeting. Otherwise, we assign a non-multitasking label. And similarly, we labeled file multitasking. And after this data processing, we run a conditional logistic regression to understand the relationships between multitasking and meeting characteristics. The second part of the study is to augment this kind of telemetry data analysis, where we have the diary study part with question, what have you noticed about multitasking in your recent online meetings, with a list of subprompts. And we run this particular study around the same period of time when we collected the telemetry data. And in total collected around 800 responses. And here's what we find. First of all, in terms of the volume of multitasking, we find from February to May, around 30% of meetings involve email multitasking, and around 25% of meetings involve file multitasking. More multitasking may be a possible result of work rhythm adaptation, and ease of turning on video and audio may encourage more multitasking. And secondly, perhaps the most interesting part of this particular study is we find a number of intrinsic meeting characteristics that are associated with multitasking. More multitasking happening in large, long morning and recurring meetings, as well as meetings with lower relevance and engagement. Let's dive in a bit. And here, the first observation is people are more likely to multitask in larger meetings. We find that the odds of email multitasking in meetings with over 10 attendees are 2.16 times the odds of the meetings with 2 attendees. And we find people are more likely to multitask in longer meetings, that the odds of email multitasking in meeting longer than 80 minutes are 6.21 times the odds of 0 to 20 minutes meetings. Those 2 observations align with our experience. But I think what is really cool about this particular telemetry data is that it also helps us to unveil some of the less obvious patterns. For example, we find that people are more likely to multitask in morning meetings, that the odds of email multitasking in morning are 1.86 times the odds of after-hour baseline, and is also higher than afternoon multitasking likelihood. And we get some kind of intuition from the diary study part. For example, one participant says, I will try to glimpse at email more if a meeting is the first thing I do for work in the morning. So that's schedule related. We also find people are more likely to multitask in recurring meetings compared to those ad hoc one-off meetings. That the odds of email multitasking in recurring meetings are 1.59 times the odds of one-off meetings. And we also get some kind of explanation from the diary study. For example, this particular participant is saying that the person has to be in a particular recurring meetings, yet the meeting itself is not that related to that person. So that person just ended up multitasking. Given all of this, what we should really be thinking about is, could this particular meeting, and especially those recurring meetings, be an email instead? And aside from that, we find a number of extrinsic meeting characteristics that are associated with multitasking. For example, people multitask during meetings to catch up on other works due to external distractions, such as software notification sound, and sometimes for anxiety relief. And in terms of what do people do in multitasking, it includes both work-related things like email multitasking, as well as non-work-related things such as browsing over social media or doing household chores. And finally, speaking to the consequences of multitasking, it involves both positive and negative sides. But our work definitely corresponds to lots of the related literature in the space on the negative consequence of multitasking, such as loss of attention, engagement fatigue, and creating sense of disrespect. It also points to some new things that is going on here on the notion of multitasking, where people have been increasingly mentioning more and more about the positive sides of boosting productivity. So taken together, this particular work, we use large-scale data to provide some kind of empirical evidence on multitasking behavior and how people conduct task switching over multiple computing platforms. And we could come up with a number of best practice guidelines for remote meetings out of our particular findings. For example, to run effective meetings, it's perhaps wise to avoid important meetings in the morning, reduce the number of unnecessary meetings, shorten meeting durations and insert breaks, encourage active contributions, and allow space for positive multitasking. And from a more product design perspectives, our study points to some interesting things, such as, so as to have effective meeting, maybe it would be good to have some kind of features so that people could really engage, like a focus mode, which doesn't really exist that much back then when we have this paper. And we also discussed papers with regard to features to help people decide which meetings or which part of the meetings to attend to. And very fortunately, this particular work not only gets some kind of attention in academia, but we also get some coverage from media such as Ford and Watt and TED. And beyond that, what is really exciting to me is that our particular work are actually being taken up by practitioners. For example, software companies such as Slack, they have been discussing our work to inform some kind of the practice at remote work. And HR departments at some leading institutes such as UC Berkeley has been using that as training material to tell people how to have better remote meeting experience. And finally, this particular way of using telemetry data to measure meeting multitasking, it has been actually informing some of the features in Microsoft product, which in this case is Microsoft Viva, about this operational effectiveness metric, so as to better understand how people work. So with that, I will wrap up the first work, which I think would be a good representative of my approach, how I have been leveraging novel data sets to generate empirical evidence to inform and to study how people work. And secondly, I would like to turn to this kind of technical method side, how I have been using technical methods and developing new algorithms to study some of the work-related problems. So the work that I would like to talk about today is team collaboration, which I got the fortune to work together with a number of really talented undergrad students at Stanford. This particular work is also motivated by some of our daily experience, that is team collaboration. So we have participated in lots of team collaboration, and as you have noticed, some of the team collaboration, it turns out to be very successful. We like the team, but on some other occasions, we just feel the team collaboration, it feels toxic, and the team just eventually falls apart. And we do not really want to work with the same groups ever again. So the thing that becomes really interesting to me is whether there are any patterns behind this notion of team falling apart or teams sticking together, whether it is possible to predict whether a team is going to end poorly. So our goal in this particular work is to classify and to predict team viability. And this notion, team viability, is a construct that refers to a team's capacity for future success. It captures the team's interest in continuing to work together and reflects team members' satisfaction towards each other. And low team viability could lead to team fall apart. We are definitely not the very first group of people to study team collaboration. But one thing that I would like to highlight here is most of the prior works on team literature, they focus on this very notion of team performance, which is definitely super important. But I would argue it's only one side of the story. Even if a team has pretty good performance, say a product team delivers the product on time and even gets pretty good outcome, that team could still have some kind of collisions or have some kind of issues, but team members do not really like each other and the teams eventually falls apart. So I would say team performance is only one side of the story. Viability is another thing that we should perhaps look more into. Yet through literature, while there has been some works in the space, we lack an understanding about the mechanisms behind team viability, and especially with regard to how team viability would be related to the team interaction process. And here's what we would like to contribute. We introduced in this work a mechanisms for classifying high versus low viability teams using only team chat interactions. And a number of research questions we seek to address here. First of all, can we differentiate high versus low viability teams by analyzing team chat interactions? Secondly, which behaviors are most strongly associated with high versus low viability teams? And finally, how much time must the team interact before we can make accurate classifications of team viability? And here's our setup. We collected complete chat history of over 660 newly convened online teams ranging from 3 to 8 people from Amazon Mechanical Turk who are collaborating on a creative, interactive, or cognitive conflict task over 10 minutes. And by the end of each task, each team member, they were asked to complete a 14-item viability instrument on 5-point Likert scale, which is presented by scholars in prior literatures. So for example, they're being asked to rate things like whether they agree with the statements, the members of this team could work for a long time together. And after they completed this particular survey, we summed each collaborator's 14 viability measures into one single individual score with a range of 14 to 70 and calculated the mean of all of the individual score to determine a team viability score, which has distribution like this. And so the task in our work translates into classifying high versus low viability teams. And to operationalize that, we divide all teams into 2 groups, either high viability or low viability based on their viability score. And we set a cutoff viability score as a varying decision threshold so that we could do tasks like, can we classify the top 10th percentile of teams by mean viability? Or in other words, can we classify the most viable teams? Or things like classify the top 50th percentile of teams by mean viability, or classify the top 90th percentile of teams by mean viability, which means can we classify the least viable teams? And here we use a binary classification model. And we specifically choose to use explainable model rather than black box model just to optimize for performance, since we would like to get a good understanding about some of the correlates that is related to this notion of team viability. And here's the specific features that we've derived through the interactions. There are 2 broad sets of features, computationally derived features and human-labeled features. For computationally derived features, we derive the features from algorithms through off-the-shelf libraries, which includes work pattern features like message counts and turn taking, as well as linguistic features such as word trace measured through loop categories and sentiment analysis measured through some usual ways of natural language processing. And for the other group of features, we have the human-labeled features. Since we do want to speak to the rich literature in the team collaboration space. So here we have another group of M-Turk workers who manually read and coded the transcript on dimensions such as whether they think this particular team has experienced social loafing or not. And here are the results that we get out of this particular approach. We find that, first of all, team viability can be indeed classified with high accuracy. Classifying the top 50th percentile viable teams yields 0.76 AUC score in differentiating high versus low viability teams. And classifying the top 10 percentile viable teams is even a higher performance, which is in this case 0.93 AUC. And I think here's something that is very interesting, that the fact that it's easier to classify the most viable teams compared to teams at other levels suggests that the most viable teams, they might share very similar behavior patterns that have been captured by our specific algorithms. But those teams that fall apart, they might fall apart for different reasons. And another thing that I think is super interesting here is shown on the right-hand side figure. Here we have 3 different curves in different colors representing the prediction results using different sets of features. And the orange curve represents using human labeled features only, the performance on using human labeled features only. And the blue curve represents the classification results using computationally derived features only. And the green curve represents the results of using both human labeled features as well as computationally derived features together. And here on this figure, the y-axis represents the classification result. And as you could see, the orange curve is the lowest, suggesting that using the human label features only, we are not able to get the similar rate of classification result as compared to using computationally derived features. And in fact, computationally derived features only, it is actually having the best performance and having interesting implications for downstream applications that it is indeed possible to use some kind of automatic metrics and algorithms to analyze the team conversations and to do some kind of meaningful classifications on the result. We also conduct a number of feature analysis and finding that active response and engagement is an indicator of high viability teams. Use of exclusive language such as but, either, except, and addressing each other in second-person pronoun, they are significantly and positively correlated with higher viability in all different situations. And here's a specific example about the high viability teams. And as you might notice, the 3 people, they've been using quite some kind of exclusive language, showing that they have been pretty considerate about what the others has been talking about, and also being very considerate about the opinion that the person is expressing. So that's kind of an explanation why we could see this kind of exclusive language being a correlate here, in that those people have been deeply engaged in the conversation. And finally, I think perhaps the most interesting and exciting part of this particular work is that we find classifications of a viable team or not is feasible after only 70 seconds of initial interaction, which in our case is only the first 12% out of the 10-minute interaction. Using the 70 seconds of initial interaction of the chat history, we achieved 95% of the accuracy from the full transcript when differentiating the top 10 percentile teams from the others. And we can observe similar types of patterns for other viability splits, which suggests that there are perhaps enough viability signals embedded in interactions of team members within short time span. So to sum up this particular work, we studied this notion of team viability, and we find this team viability is driven by underlying mechanisms that are common across different team setups, task categories, and can be largely captured and explained by team member work and linguistic patterns that could potentially be captured through automatic algorithm. And when we think about its potential implications for designs or product, it could become quite exciting. It could enable things as early detection of low viability teams. And so beyond that, it could enable things like recommendations for team members before a team gets into trouble. And that would be very different from the current way of sensing the team status through survey, which can only be done in a post hoc way. And of course, in this particular work, the data is kind of limited to very specific setting. We're only looking at online teams working on short tasks, but as follow-up work, we have actually been working together with companies and working on more realistic data through software engineering teams. And we find our approach could still largely work. And that's very exciting. And I hope this particular work will get published very soon. And finally, we have a working algorithm prototype at this particular website, viability.stanford.edu. If you have some kind of chats of your teams, you can check out whether it is viable or not. And finally, I would like to talk about my work that is the design side, which in this case, I would like to talk about our recent work on using generative AI and how we have been coming up with a tool and system and evaluate how does that work in practice for a specific group of knowledge workers, researchers. So this particular work, I get the fortune to collab with two other wonderful colleagues at Stanford, and it's currently under submission. So the central theme of this particular work is about feedback in science. Why feedback is important in science? Because it sparks discoveries by melding insights from different people, and it also lays the foundations of rigorous research. And as many of us might be familiar with, there are multiple channels of doing scientific feedback, including one of the most important way through peer review. And of course, there are other channels such as conference discussions. But in this work, I'm mostly talking about peer review type of feedback. As some of us may also notice that the current way of conducting scientific feedback is actually flawed. The challenge comes from the increasing number of paper submissions. For example, in computer science, and especially in machine learning these days, there have been increasing number of paper submissions every year. And ICLR is the top machine learning and one of the most important deep learning conferences. A number of years ago, it only has a few hundred submissions, but last year, it has over 5,000 full paper submissions. And the direct consequence of the increasing number of paper is that there have been overloaded reviewers, and it's been increasingly difficult in securing qualified reviewers. And we have seen lots of complaints, both over social media as well as discussions over academic publications, discussing this kind of issues of challenging us getting quality feedback. And on the other side, scientific feedback also has implications for scientific equality. We currently have the issues of under-resourced researchers. They have even harder times getting timely and quality feedback, especially for junior researchers, researchers from non-elite institutes, or researchers from resource-limited regions. Through conversations with them, we've heard things like they are in journal field and they submit papers to journals and the papers get desk rejected and they didn't receive any feedback at all. And they suffered a lot how they could revise their papers to get into some other places. So clearly, scientific feedback is also kind of like a resource that is not evenly distributed. And our specific idea and the thing that we're pursuing here is wondering if it is possible that large language model, given all its significant contributions in different types of applications, could it be helpful in this kind of research feedback? So here's the tool that we've built. It's actually pretty straightforward. The idea is the authors could upload their own papers in raw PDF format. And then we parse the PDF into specific content. And then based on GPT-4 and our prompt, we could create something that it would look very similar as what people would get from peer review. So we built this particular tool, and we really want to understand to what extent it is helpful or not. And we conducted a mixed methods design study here, which includes a retrospective evaluation and a prospective user study and survey. And here, due to the limitation of time, I will mostly talk about this retrospective evaluation, where we compared what has been generated by AI versus what has been generated by human. So here, to do this kind of retrospective evaluation, first created two large-scale data sets. The first data comes from Nature Family journals, including over 3,000 papers and over 8,700 human written reviews. And the Nature family journals include not only Nature's, but also a number of subjournals under Nature, like Nature Human Behavior and Nature Communications. And another data set that we use come from ICLEAR conference, which is the top machine learning conference and one of the most important computer science conference. In total, we collected over 1,700 papers and over 6,500 human reader reviews. We selected two large-scale data sets for multiple reasons, but specifically try to cover as many different types of papers as possible. Since Nature family journals, although it covers different fields and covers from niche to high-impact journals, it is limited in the sense that it only contains reviews from a number of accepted papers. For ICLEAR datasets, it's on the other way around. It only focused on one specific field, but it contains review of both accepted and rejected papers, since it's held over the open review platform, where all papers will get the reviews public. And to evaluate to what extent the AI-generated feedback overlaps with the human-generated feedback, we propose a retrospective common matching pipeline, which is actually also very straightforward and simple. The idea is to again leverage GPT-4 using the large language model. And we first do a summarization over either the AI-generated feedback or the human-generated feedback, so as to get the major points, major comments, and key comments people or the AI have been raised. And then we use GPT-4 again to compare the similarity of the key points generated by AI or human, and to calculate to what extent they are similar to each other, so as to calculate a matching coefficient. And we validate this particular approach through human verification, which proves to be a pretty good performance. And based on this kind of matching pipeline, here are the findings that we get. First of all, we find that large language model feedback significantly overlaps with human-generated feedback. Around 30% of the comments raised by GPT-4 overlap with comments from one individual human reviewer. And to put that into context, that's roughly the same level of overlap between one human reviewer versus another human reviewer for the same paper. We observe similar patterns over the ICLEAR datasets. And we find these trends holds for different subfields on the Nature family journals. And another interesting thing that we find when analyzing on the ICLEAR datasets is that we find the overlap between GPT-4 and human reviewers is actually larger for the weaker papers. There are more overlaps between AI and human for rejected papers, which is interesting in the sense that this fact points to the fact that large language model feedback could be particularly useful for those papers that needs more attention and needs more time to get accepted. One other analysis that we did here is try to figure out to what extent large language model is generating paper-specific feedback. Because you might be wondering, is large language model only generate something very generic, like this paper lacks novelty, that it is applying to all the paper? Is that the case? To rule out that possibility and to analyze this particular point, we do this kind of random shuffling exercise. Basically, the idea is if the feedback is generic and can be applied to every paper, if we shuffle the feedback, then it is likely, very likely, if it's generic feedback, it will also be applied. It can also be applied to other papers as well. So we'll see no differences in overlaps if the feedback is generic. But after we randomly matched the papers and the reviews, we actually find significantly decreasing overlap after shuffling, indicating that the large language model feedback is indeed paper specific. And some additional analysis show that comments raised by multiple human reviewers, they are more likely to be hit by GPT-4, or basically, in other words, those points that people have consensus on, arguably more important points, they're likely to be hit by AI. And finally, we find GPT-4 tends to focus on certain aspects of scientific feedback that is different from human. People talked a lot about novelty of the paper as well as papers miss some citations. But AI mostly focused on implications of research, as well as things like ad experiments or more data sets. And our prospective user study further validates these results. We send out this particular tool to a number of researchers in different US institutions and try to get a sense of how people think about those feedbacks on their own papers, whether it's helpful or not. And we heard more than half of the users found GPT-4 generated feedback helpful or very helpful. And over 80% of them found it more beneficial than feedback from at least some human reviewers. And this perception of large language model feedback helpfulness is kind of consistent across different groups, whether it is undergrad students or faculties or people, or in other words, people with experience or without much experience with research, they find some kind of merits in such kind of tool. And we also heard more than 70% of participants think there is at least some alignments between large language model feedback and what they think or what they would get from actual human reviews. So taking this together in this particular work, we designed and come up with this particular tool to provide scientific feedback back to the authors. And we think this could be especially helpful for people who lacks access to qualitative scientific feedback. And when timely expert feedback is not available or in early stages of manuscript preparation, people could be using this kind of tool to give first round of feedback for themselves as to improve.
Have this class at 2 o'clock. It's 2 o'clock, Sergeant.
Yeah, cool. Yeah, and I'm right at the end of this talk, but thanks so much for being here about this.
Thank you very much.
Thank you.
Right, so.